start by an introduction to hyperbolicity.
Okay, so thank you. So indeed, I will try to introduce the basic concept and conjectures and tools and strategy developed in the field in the last decades. So to start, maybe if you try to look in the history when people study questions related to what we call hyperbolicity in complex geometry, you can probably go back to classical statement of Liouville. Classical statement which states that if you take a holomorphic function from C to the disk, then such a map is constant. So this is the first example of complex hyperbolic variety. In fact, it's kind of the key object in the theory. So now if we start to move to compact variety, so you start in dimension 1, considering X a compact Riemann surface. And so if the genus of X is greater or equal than 2, then you have the same statement is constant. And in fact, you can deduce this statement from the previous one if you use the uniformization theorem. So you consider the universal cover, since it has genus greater than 2, it's the disk. And so any such holomorphic map we lift here, and by Liouville it has to be constant. Okay, this is a nice proof. It uses a strong theorem, but if you want to extend this kind of statement to higher dimension, of course you do not have uniformization. So I want to give you another proof which does not use uniformization. And in fact, this proof will essentially be the one that we want to generalize to higher dimension. So then you want to use some statement from algebraic geometry. So proof without using uniformization. So the idea, in fact, which was introduced in the last talk yesterday, is that hyperbolicity has to do with the positivity of vector bundles. And what is the natural vector bundle associated to variety? It's the tangent or cotangent bundle, right? So here, if another incarnation of this statement is that the canonical bundle, which is the same here in dimension 1 as the canonical bundle, is ample, is positive. Right? So we can find differential forms. So in particular, you can certainly find an integer such that this bundle is globally generated. And this L is ample. So you can find such global differential forms. So you pick so generated by global sections. Let's call them S1 to Sn. Okay, and now you will use this section to cook up a metric which has negative curvature. And this will do the job. So, metric, you construct a metric with negative curvature. It's very easy. So the metric is constructed like that. So pick a tangent vector. So you will, by definition, define the square of its norm to be the following quantity. So you use the differential forms, and you use a metric on the line bundle L. So this is a metric, and it's not difficult, if you compute the curvature, to see that it has negative curvature. And then the statement, the conclusion, is just an easy application of the classical Alford-Schwarz theorem, which tells you that if this was non-constant, if you have the metric, this would give you a metric of negative curvature on C. It's not possible. Okay. So this implies the same state has to be constant. So this proof is easy, but it has the great advantage that you can opt to generalize it to higher dimension, okay, compared to uniformization. And in fact, already here you see all the key characters of the story. So the situation is completely understood for compact Riemann surface. So we can completely characterize a compact Riemann surface satisfying this property. So you are given a compact Riemann surface and you want to decide if there is or not an entire curve. So this is completely understood, thanks to classification also. So in this case, so certainly there is a non-constant. In this situation, the elliptic curve, certainly also there is one. And we've just proved that in this case, there is no. Okay, so there is a complete characterization of compact Riemann surface with this property, and so more generally, so I will use the following notion then. So if X is a complex variety, not to repeat each time holomorphic non-constant, I will call that an entire curve. Okay? So entire curve is by definition a non-constant holomorphic curve from C. And so you define definition. So now there is a lot of different notions of hyperbolicity, and you usually want to compare them. So I will just focus on one, which is what we call Brody hyperbolic. Because Brody made important contribution to the study of this topic. So X is called Brody hyperbolic if X has no entire curve. Okay, so this is a general definition for any complex variety. Okay, so the best now is to give more example or non-examples. Okay, so we've already seen one. X compact Riemann surface genus 2 is hyperbolic. So now from this, you can already construct higher dimensional example. Just take product. Very easy. And you can also make an interesting example, even though we do not have uniformization, so we can still use the same idea. And so in any dimension, if you can construct, let's say, a smooth compact quotient of a bounded domain, this will be trivially hyperbolic, right, by the same argument. And in fact, this kind of variety are very important and show up in algebraic geometry as moduli spaces. They are very common. It's also important somehow to give non-examples. So, for example, the generalization of the elliptic curves, genus 1 curves, are all complex tori. They are certainly not hyperbolic. And you can look at subvarieties of complex tori. And this has a very nice characterization. So X is hyperbolic if and only if X does not contain subtori up to translation. So X does not contain a translated subtori. So of course one direction is easy, the other is not. So it's a famous theorem of Bloch-Ochiai, which gives you the nice statement that if you look at the Tarski closure of an entire curve in a complex tori, this is a translated subtori. Also, important to note is that hyperbolicity is not a birational invariant, right? So if you start with something hyperbolic, and let's say of dimension at least 2, you pick a point and you consider the blow-up. So certainly this will not be hyperbolic, right? In the exceptional divisor you have entire curve. So this is not a birational invariant. So from the point of birational geometry, it's not very good. And this is why people have studied more general notion, allowing exceptional set. Okay. Also, from algebraic geometry, you know that if, so let's say X is projective, and suppose there is a projective curve inside X, such that it has a negative intersection with the canonical bundle. So from a classical statement, Benenberg statement in algebraic geometry, you can cook up a rational curve. It's even algebraic. So certainly, X is not hyperbolic. So this also shows you that positivity of the canonical bundle has to be in the story. And now comes somehow the main example. So I'm very glad to the speaker of the last talk yesterday who introduced this class of varieties already. So this is the generalization of the variety with this property. So varieties with ample cotangent bundle. So varieties with ample cotangent bundle. Okay, so you take X projective and ample cotangent bundle, and you take an ample line bundle on it. So these varieties are hyperbolic. So I will give you the proof. The proof is in fact the very same proof as here. Very easy. So you just take section okay, so you can find a section here. So the nice way to see that geometrically is the following. So as we have already seen yesterday, so ampleness of the cotangent bundle is defined by the ampleness of the tautological bundle on the projectivized bundle. So here I take the projectivization by line. So this is a projectivization of Tx. And so you have the O1 here, okay? And you can consider the following line bundle. So on the projectivization, and so from the assumption, you can certainly make for M sufficiently large this one ample. Okay? And so now the geometric picture is the following. So if you have an entire curve here, you can consider its lift here. Let's call it F1, so very easy definition. You just consider the lift by given by the derivative. Okay? So you have a natural lift to the projectivized tangent bundle. And now, okay, section here are in fact the same as section here. Okay, and so you do the same as before. So from this section, section here, you construct a metric of negative curvature. So the formula is the same. I will not write it again. So you have a metric on the tautological bundle with negative curvature. This is, so you produce the metric exactly from the sections. And so now you just have to remark the following to do the same argument. you remark that the derivative of f, in fact, give you a morphism here, okay? It's tautological. And so the same argument give you that if you have a non-constant map, so this will give you a non-constant lift, and you would, by pullback, produce a metric of negative curvature on C. And you conclude again by alpha Schwarz. It's the same. So you conclude that F is constant. Okay, so in fact, the proof gives the more general statement that would be useful after. So the proof gives, in fact, that even if you don't start with something ample, okay, so you can consider the same diagram, like I did here. Okay, so for any x so for any variety and any m, the lift has to lie in the base locus, in fact, of this bundle. Okay, so in the previous statement, this base locus was empty because it was ample, cotangent bundle. But in general, even if it's not ample, the same proof, because you construct a metric, okay, it has a degeneracy locus, the metric, that it works, and tells you that the lift has to lie inside the degeneracy locus of the metric you constructed. So this tells you geometrically exactly this fact, is that the lift has to lie in the common zero locus of all the section of this line bundle. Okay? So this is what comes out of the... Okay, so there is this nice class of hyperbolic. So of course, the remark is that certainly the converse is not true. So hyperbolic does not imply ample cotangent bundle, except in dimension 1. So the remark is that hyperbolic does not imply. So this is certainly not a good characterization, algebraic characterization of hyperbolicity, so just take product. This is hyperbolic, and this does not have ample cotangent bundle. But, so people have looked for algebro-geometric characterization of hyperbolicity, and there is another property shared by varieties with ample cotangent, which is quite interesting. So this is the following. So if you have a variety with ample cotangent bundle, then any subvariety is of general type. Any algebraic subvariety is of general type. So this means ky big. So the asymptotic growth of global section of twist of the canonical bundle is maximal. There are many, many sections. So this is an interesting property, and this is exactly the property conjectured by Lang to characterize hyperbolicity. So this is the conjecture by Lang. First, big conjecture. is that, so you take x projective, x hyperbolic, if and only if all subvarieties y in x, of course including x itself, is of general. Okay? This is a very nice statement which is supposed to characterize an analytic property, hyperbolicity, by purely algebrogeometric tools. Right? Just check if you have sections. Okay. And one could thought, is it possible to relax that and maybe ask that only x is of general type? No, this is not true. So general type does not imply hyperbole. Okay, this is very easy. You just, so of course, nice examples of first projective varieties to consider, which I will consider after, are hypersurfaces in projective space. So if you consider, for example, Fermat hypersurfaces, in Pn plus 1, so being of general type is very easy to characterize. Does that the degree has to be strictly larger than n plus 2. So this is of general type, but certainly this is not hyperbolic, right? It contains lines. But this one satisfies even kx ample, but not hyperbolic. Okay, so hyperbolicity is, you need really constraint, but still, you can still try to characterize what general type implies, maybe something weaker than hyperbolicity. And this is what people conjecture. So the other big conjecture of the field is the so-called Green-Griffiths-Lang conjecture. So all these conjectures are widely open and are very leading motivation. Okay, so what can we expect if we just ask general type? Some weak version of hyperbolicity, so we call that pseudo-hyperbolic. So this means that maybe it's not hyperbolic, so you have entire curve inside, but they cannot cover the variety. They have to lie in a fixed proper algebraic subvariety. So there is a proper algebraic subset in X such that all entire curve lie in Z. Okay, so these are two main conjectures, and then people try to focus on particular example as here hypersurfaces. So important conjecture here was due to Kobayashi. So consider hypersurface of degree d in Pn plus 1. Of degree d. So, of course, you can consider this conjecture, and it tells you that if d is greater than n plus 2, it has to satisfy some pseudo-hyperbolicity, but Kobayashi conjectured more. He said that if you increase, again, the degree, you can go to hyperbolicity. Of course, not for every hypersurface, as we see with Fermat, but for generic ones. So, the bound is conjectured to be 2n plus 1, and at least 2 generic, mean in the parameter space of all hypersurface, you have to remove a proper one. And then in this open, hypersurfaces should be hyperbolic. Okay? So there was a lot of work on this, so I will mention names after because I will explain you the tools and strategy to attack these conjectures. Okay. So, yeah, now we go to the strategy. How to, somehow we just have to elaborate on the proof I've explained you. So the proof for ample, you have to somehow use more general tools, but the idea is exactly there. But in general, for example, in the case of hypersurface, you cannot expand even to get one non-zero symmetric differential. You can show by vanishing theorem that there are simply no global symmetric differential on hypersurface. So you need to find something else. But what is a symmetric differential? It's a differential operator of order 1. It acts on first derivative of jets. So the idea is, well, let's look if there are operators acting on higher derivatives. This is what people have tried to do. So this is the whole setting of that we have already seen in the first part of this week of jet spaces and differential operators. So this is the place where techniques from Singularity, which were explained, and this topic of hyperbolicity they will meet here. So, okay, so we start with any complex variety of dimension n. And so we consider the usual jet space, K-jet bundle. Okay, so we've already seen it, as I said, just a generalization of the tangent bundle. So for K equals 1 is just a tangent bundle. And so we want to consider functions on these jet spaces which will be encoded in a vector bundle. So this is the so-called Green-Griffiths bundle. So denoted like that. So K will be the order of jets you consider, order of derivatives. M will be a degree of polynomial counted with weights. And this is because there are now several bundles to consider. Here I consider the first one introduced by Green-Griffiths. So this is a vector bundle. So I will give you what are the local sections. So if you consider local section at a point x. This is just, by definition, polynomials. Okay, this is polynomials on the jet space at x. So polynomials on the jet space at x. Okay, this is the k, go on jk, and of weight 1, m. Meaning that there is an action of C star there is an action of C star, so you want to ask that if you take a reparametrization by dilatation by lambda, so it, out of the derivative it goes to the order of derivative like that. You want this. Okay. So this is just a way to measure the degree of the polynomial, but with this weight. Okay. Okay. So this is really just a generalization to any order of a symmetric differential. Okay, if you take k equal to 1, this is exactly the symmetric power of the cotangent bundle. Okay, and now the hope is that if you go to sufficiently high order, you can construct such non-zero sections. So we need an analogous statement as this, which is true. Is the following statement. So of course, it's a bit more technically elaborate, but the idea is exactly the same. So the statement tells you that if you can construct non-zero sections, so you take, suppose you can find such an operator, okay, with this twist of minus and number, then for any holomorphic map from C to X, sigma of F, if you prefer GK of F, is identically 0. So what does it mean geometrically? It's exactly the same. So you have X, you have GK of X. As before, of course, if you have a map, you can construct a lift to any jet space by considering the corresponding derivative. Just the collection okay, so you can call this the K-jet lift. Now, such a section is by very definition just a holomorphic function on jet space. Okay, so it's a holomorphic function here. Okay, and what it tells you is that the lift has to lie in the zeros of this holomorphic function on the jet space. Okay, it's another way to see this. And very concretely, it just says that your entire curve satisfies an algebraic differential equation of order k. Okay, this is, you see, really, it's just the generalization of this. You replace the tangent bundle by the k-jet space. And you construct the analogous object corresponding to symmetric differential. Of course, the complexity explodes. Okay? This space has increasing dimension. And so it becomes more and more complicated to see, is there any section? Is there any non-zero section? Okay. But at least I hope you see the picture and you immediately find, I guess, you guess the strategy. How to prove that a variety is hyperbolic. The strategy now is very simple. At least a scheme of strategy. Showing it is, of course, another story. But now, okay, so now the strategy is kind of clear. Strategy to prove, let's say, Green-Griffiths-Lang conjecture is the following. So it's always like this, jk of x. And now inside this, okay, here I've stated the statement for one section. Now you take all section and for every n. Maybe there are a lot of sections. Don't know. So anyway, inside these jet spaces, you have a collection of all these sections. You take the zero set, you take intersection over all n. Okay? And the statement tells you that your entire curve has to lie inside this. Okay? Your entire curve has to lie here. So now you just project. Okay? Project on x. You have natural projection from stage k to stage 0. And of course, this tells you that your entire curve has to lie, let's say, in the Green-Griffiths-Lang locus, which is just the intersection now over all k of all these projections. Okay, this is a trivial consequence. Of course, now there is two problems if you want to prove Green-Griffiths-Lang. The first one is two important problems. First one is, well, is there any section at all? I told you that, for example, for hypersurface, here at order 1, there is no section at all, 0. So, prove that these spaces are non-zero. So you see, not only you want to produce section, you want to produce some with a twist in the, so with additional 0 a number divisor. So, but maybe the hope is to prove this for large k. Okay, you want to take k large. And the second one is, even if you have produced this, all this 0 set could well cover x. So you have to prove that this is different. Okay? So here is the way you want to proceed. So let's talk a bit about. So we just introduced. I think it's the topic of Benoit, to go into detail in this first problem, and Joël about the second one. Okay, but I will introduce a bit their talk and explain. The strategy. So, okay, so the first problem is solved in some sense by very nice theorem of de Mailly. In the setting of the Green-Griffiths-Lang conjecture. So de Mailly proves the following. So if X is of general type, then indeed there exists such a large order where you can find non-zero sets. Okay, so this is a very nice statement which tells you that indeed with this algebrogeometric condition, you just suppose that you have top differential form on a variety, or many in the multiple general type, then you can produce such a non-zero differential operator. So of course this statement comes after the work of many people, especially in the case of hypersurfaces before. So Diverio did some work, I did some work, and then I think the optimal statement for hypersurface was due to Joël.
Using your ideas and your techniques.
Okay, thank you. And so he proved the statement that indeed the degree bound to be of general type, so greater than n plus 2, you can produce differential operators. Okay? Okay. So Benoit will detail all this. And I want maybe to focus more on the second point. Of course, as you guessed, but I want to insist, it's really non-trivial. And in fact, in a strong sense. So there was in the community really a great belief that this strategy could work in general to prove Green-Griffiths, and we realized that there are some trivial examples showing that this strategy can fail. Okay? But the examples are in some sense so stupid that people did not look at them to test the strategy, because they were hyperbolic for other reasons. Okay? So there exists X, general type plus hyperbolic. Such that this Green-Griffiths-Lang locus is X. So there is no way to prove any constraint on the entire curve using this strategy. So these examples are, so you can construct many of them, but the most trivial one has already appeared when I told you that some varieties did not have ample potential bundle. In fact, you just take the product of two hyperbolic curves. So this was an observation we made with the absent Simone. So this very trivial example is, of course, hyperbolic. It's general type. But you can show that the Green-Griffiths locus is the odd variety, and the argument, so I don't think I have time to state it, it's very easy. You just use the fibration, so the foliation. And you restrict your differential operator in the direction of this foliation induced by fibration, and you show that it has to be 0, just for simple Kodara dimension reason. So this is a very bad phenomenon. Hopefully, this does not appear for hypersurfaces. Okay, so the strategy works for the Kobayashi conjecture, but you have no hope to make it work in general for the Green-Griffiths line. At least like that. So let's focus on the Kobayashi conjecture. Okay, so you consider hypersurface of degree D. Okay, so now I tell you a bit the history, because there are many names. So for surfaces, it was done by McQuillan, De Mailly and Gould. Pound then came. And they proved the conjecture for degree at least 18. Okay, so generic surface of degree at least 18 is hyperbolic. In dimension 3, I did it showing the Green-Griffiths version of this kind of degree, and in fact, an easy remark of Di Verio and Trapani. In fact, it was like premonitory of Eric work, is that in this case, it's very easy to show that the Green-Griffiths version implies the Kobayashi version, just for some simple codimension. So they show, in fact, that my statement, where I prove Green-Griffiths, implies, in fact, Kobayashi hyperbolicity. Okay, and then we tried with Simone and Joel to implement this strategy, but important input of Hsu. Okay, so Yang-Tong Hsu entered the story, very important, to help us with the second point. So with Di Verio, Joel, we proved that for some effective, so now it's any dimension, we proved with some effective bound, then we have the Green-Griffiths version, and then so with after came the work of Eric, Riedel, and Young, showing that in fact, if you have Green-Griffiths, this gives you hyperbolicity. So both statements give you now one proof of Kobayashi conjecture with this large degree. Okay, and then there was an independent proof by Damian. There is a C in your name? No. So a completely independent proof showing directly the Kobayashi conjecture without passing through this strategy. And then with the complement of Yadeng, there was also an effective degree, probably something like n to the n, something like that. Yeah. Okay, so this is the history of results. And now, as I say, I want to explain you briefly the strategy that Joel will detail. So this is the strategy of Hsu, Yang-Tong Hsu, to prove this Green-Griffiths statement. So he introduced a very elegant way how from one section you can cook up other sections. And his idea is in fact also not completely new. It was inspired by work of Voisin and Hein, who somehow did the order 1 case. Okay? So the idea is the following. You will use vector field on jet space to differentiate your first equation to get new one. Okay? So his idea is you want to use vector fields on the total space. So you need to work on the total space of jet bundles to differentiate sections of this bundle, which I recall are nothing else than function of jet space, and you will differentiate them with vector fields. This will give you new functions. To produce new one with less zeros. So you want to decrease, of course, you want to do that in an intelligent way so that you cut this zero space. You want really that the new section you produce decrease the dimension of this space so that at the end it will not cover your variety. So there are of course serious difficulties to do that also. So the idea, which was used by Hein and Voisin, is very nice, is to consider the universal hypersurface. Consider the family of all hypersurfaces. So this is the parameter space of the greedy hypersurface in Pn plus 1. Okay, and now you will produce vector field on the k-jet of this. Okay, so the idea is like this. You are in GK. Suppose you have produced a first section. Okay, so there is a first zero set in your jet space, and now you want to differentiate to get less zeros. So this is a polynomial of degree m. So you know that if you differentiate in a good direction, you will produce something non-zero at this point, right? But you see that you have to control the direction. So there is a need to be able to find vector field on your jet space which pick in the good direction. So this is why you need a global generation statement. It's not only to produce vector field, you need to show that this is globally generated. Okay, at a fixed point in the jet space, you want to be able to differentiate in some directions so as to produce. Of course, there are some difficulties. First of all, this statement, as stated here, is not true. So you have to consider meromorphic vector fields. So introduce poles. Joel will explain that. And So this comes out, so there are, so just, okay, I'm over. So just to say orally maybe, so there are two problems. As I said, so the first one comes from poles of vector fields, which you will have to control, and moreover, global generation will be shown outside of some proper algebraic subset that Joel will describe. And since you have poles, there is a second problem coming, is that you remember to use the vanishing theorem, you need a twist. But if you add poles, you add some positivity here, so you decrease the negativity. And imagine you differentiate with meromorphic vector field, you add poles, and then these disappear. You cannot apply the theorem anymore. Okay? So you need a subtle control of the contribution of poles, so that when you differentiate, you do not kill the contribution of the negative part. Okay? And as Benoit, I think, wanted the statement, I will finish with that, is that what comes out of all this control is that if you can produce a section in, so here the order will be the dimension of the hypersurface. And, okay, and you need a twist, not arbitrary, but something like that. So in the end, what comes out of all this subtle computation is that if you can produce a section which has this, be careful, you also see that the vanishing depends on the degree, then the strategy works. So in the end, it comes out that if you have such a section, then you have proof Green-Griffiths for hypersurfaces. Okay, so I think I have to stop.
In the theorem with domain over there,
Yeah.
is there any condition for M?
There is any, yes, sure. You also need to take M large.
Yes. Every day,
Yeah.
for enough large.
Yeah, just concentrate on the, it's like, even for order one, you need to take probably M large. So the statement, as I stated, is just that there is an order of jet where you can get a section, but as you say, probably you have also to take M large. Yeah.
You were talking about those examples of varieties like products where the Green-Griffiths locus is equal to the whole thing.
Yeah.
Is it expected that that's basically the only obstruction, or do we have a...
In fact, we have a whole family of examples which are built on, in fact, quotient of bounded domain.
Okay.
So we show that there is like a dichotomy. So either the domain is the ball, and there everything works fine because it's sample. Okay? Or if it's a bounded symmetric domain which is not the ball, it fails. And then you use a more elaborate argument of foliation thanks to work of Mock. So on the product, it's easy. You see foliation on the product easily. But on quotient of bounded symmetric domain, which are not the balls, you can see some tautological foliation on the projective vice tangent bundle that you do not see on X. They live on the projective. But the same argument works, thanks to work of Mock, is that if you restrict your jet differential in the direction of this tautological foliation, they have to vanish. And so you show that they cover all varieties. So you have many, well, at least many.
Yeah,
You have some series of examples.
There are no more questions.